Start.
Hello, everyone. Me, Krishna, and we are going to talk about our effort to unravel the non-deterministic query conundrum for Prestissimo verification at Meta. And next slide. So, what is a non-deterministic query? So, non-deterministic queries are queries that, for the same set of input records, return different results over different runs when executed on Presto. So, queries containing non-deterministic function are non-deterministic queries. If limit or table sample Bernoulli is in the query shape, the returned results are also non-deterministic. So for this talk, we will focus on queries with non-deterministic functions. Then why non-deterministic function is important for Presto correctness verification and release. For correctness verification, we run the query in a control environment, usually the current release, and in a test environment, usually the next release, and compare the results. So the presence of non-determinism makes the execution result not comparable. So this is the problem that we are addressing. So when we look at the entire workload that Presto is handling at Meta, non-deterministic queries account for roughly 20%. So for reliable release, we need to get the correctness signal for this significant portion of workloads. So the next slide. And then in what ways that some functions could return non-deterministic result? This will help us identify non-deterministic function. So first, some functions are sensitive to the order of input records, like first value array aggregate. And the order in which the input record arrive is non-deterministic. Then second, the scheduling of splits or the different number of shuffling destination or the multi-threaded execution of operators all could possibly lead to different sets of input records arriving at a driver. So this would also affect the operators whose result can change with a different set of input records. For example, the limit operator. And additionally, functions based on some functions based on sketching algorithm can also give non-deterministic result due to the difference in implementation in different languages for engines. And last, some functions are non-deterministic in nature. For example, random, shuffle, or null, those functions. Yeah. Next slide. For this talk, we are going to use a non-deterministic function, maxby, as a running example. As the example shows, when there is a tie on total price, which clerk ID is returned is non-deterministic. So this example shows how we utilize Presto Verifier to verify queries that have a maxby function today. The Presto Verifier sends the test case query to both the control environment and test environment and keeps the results in a temporary table. It then calculates the checksum of every column. If a column checksum match, the verifier determines that the test environment execution returns the correct result. In this case, as maxby can give non-deterministic result on either run on environment, it's uncertain that the corresponding column matches or does not match. Yeah, so this is our problem. Next slide. So then how we solve this problem? Our solution is to utilize a Presto Verifier and a Presto Query Runner enhanced Fuzzer altogether to tackle this problem. So we extend Presto Verifier with the feature to substitute non-deterministic function with a deterministic function. This allows us to verify at the query level the entire query shape excluding the non-deterministic function. Then to verify the correctness of non-deterministic function itself, we rely on Velox Fuzzer, enhanced with a Presto query runner. Yeah, next slide. Next, we will talk more about how non-deterministic substitution works with a Presto verifier. Yeah. First, how we pick a substitute. So we need to come up with a function substitute that returns the same type as the original function to keep the original query syntactically legal. The objective is to make the non-deterministic function expression as well as all its ancestor nodes of the query AST return deterministic value in order to make the entire query deterministic. Column types must remain the same, but column value can change. Looking back at our example, the max colored by total price. A deterministic substitute can be max colored by the hash of color. The two functions return the same type. And with a carefully selected hash function, we will get no two color values to have the same hash. This breaks the tie. So the hash function here needs to be orderable and has no collision. Yeah, next step. So then how we build the support for non-deterministic function substitution into Presto verifier. We allow the user to pass a pattern to the verifier by a parameter for any function and its substitute, like the example shows. So for a test case query, the query rewriter component traverse the AST tree and identify all function call nodes that have a substitution defined. It then perform the substitution and reconstruct the AST tree. The red graph shows how the max by function call is substituted by the defined pattern. So the next step, I will then pass it to Krishna to share how we leverage Velox Fuzzer for a correctness verification.
All right, thank you, Guy. To summarize, verifiers substitutes non-deterministic functions with deterministic ones. We run the substituted query in control and test and validate the results are equivalent. However, we still need some means of verifying that the non-determinate function is correct. And here, Velox needs to guarantee correctness of these UDFs, UDF, etc. So how does Velox do this? Well, we use fuzzer-based testing. Essentially, we generate a lots of random data as input and run this for some aggregation of Velox, and then also run it against a source of truth. Then we validate that the results are equivalent, and if not, we know that there is a bug. This works well enough for deterministic functions. For non-deterministic functions, we can't use our current means of validation as the results produced by the source of truth can be different. For this, we use custom verification and we determine correctness based on properties of the non-deterministic function being tested. First testing is inherently random, and thus higher chances of bugs are found the proportion to the longer compute runs. Thus, we run this at PR time, and we also schedule fuzzer runs to just increase the odds of us finding a bug. Next slide. Let's now go into a bit more detail on how fuzzers work. Here I'm going to how the aggregate fuzzer works, but all the fuzzers generally follow the same principles. We have a set of UTF signatures. We filter the set if required. For some reason, say we don't support types, certain types, etc. We pick one of the remaining signatures at random, and then we use the RNG to generate random plans and expressions. Then based on the signature, we generate random vector data and then execute them and validate the results. Next slide, please. So what are the main components of the aggregation fuzzer? We have the vector fuzzer. This generates random vectors if provided a vector type. We also have a component that generates random plans. Then we have the reference verifier, and that is the source of truth. At the moment, this can either be DuckDB or Presto. Finally, we have custom input generators and custom verification, right? We need custom input generators since you see oftentimes randomly generated data does not properly test certain functions that require that data be present in some structured format. Right? For in these cases, we use custom input generators. There are several examples of this, like if you have regex or something like that, you would want it to be structured in a certain format. Custom verification is also used for non-deterministic functions to verify that the results using certain properties of the function being tested, because often for in these cases, the result return source of truth and what is produced by Velox will not necessarily be the same. Nevertheless, the result is still correct. Next slide. So let's look into a little more detail about the plans being generated. For each chosen aggregation function, a large number of plans are generated. Our only single aggregation is verified against the source of truth. By verification, I mean the results match on Velox and the source of truth. Once this is verified, we use the results of the plan to match the results of all the other plans and ensure they are the same. Summarize, we start off with single aggregation, right? We compute a result in Velox and use the same plan, single aggregation plan, run it in the source of truth, get results, compare. And then if they are same, we know that that's correct. And then we run or generate a set of other plans and we compare this to the verified plan. Internally, the fuzzer generates plans based on certain decisions it takes randomly. Yeah, the universe of all possible plans is rather large. And so we randomly create a subset of plan based on the RNG. For example, in this picture, we can see that based on the choice of table scan or not, a different set of plans is generated. All right, next slide. Okay, let's look into a little more detail on the reference DB. Currently, we support only DuckDB and Presto. We are trying to migrate to using Presto exclusively and are slowly moving towards that goal. DuckDB in the process is in the process to the other, whereas Presto runs out of band as a sidecar process. That is, DuckDB runs as a part of the fuzzer itself, whereas Presto runs outside because it's not a C++ application. Right? We use Presto Query Runner for the purpose of communicating with Presto. It writes out data as a dwarf file locally, and then it creates a temporary table on top of it. Now, plans are converted to SQL, and then they are run against this temporary table. This means this has certain limitations, obviously. For example, right now we can only run like one query at a time. But this is not a problem in practice because the bottleneck is not Presto or the or source of truth. We are bottlenecked on the Velox side because you did for any one plan. As you can see, we generate a lot of other plans and we verify and execute and verify all these plans against the source, against the results verified by the source of truth. So this works quite well in practice. Next slide. Moving on, let's get back to the generation of input data. For most functions, we use vector fuzzer, and it generates the data based on the type signature of the function being tested. However, in certain cases, functions expect the data passed to them to have certain structure. Otherwise, we do not test the function. It rejects the inputs passed, right? In cases such as these, we use custom input generator, which requires you to implement one function. And you can see the for signature of the function below. And it takes in the type of vectors to be generated. You see that vector type is passed. It also passes a fuzzer, which you can use to generate random data in case you need it, and RNG and a memory pool. We use this currently for some functions like min by, max by, etc. The approx distinct functions, etc. Next slide. And at the other end of the spectrum, for non-deterministic functions, we rely on custom verifiers. Again, here we use custom verifiers where the results need not be 1:1 with the source of truth, right, to be correct. In cases such as this, we rely on the property of the function to determine what the correct results are. So it depends on the nature of the function you are testing. So, for example, an approximation will have certain properties, whereas a max biome will have some other properties. The API for custom verification requires you either to implement a verify function or the compare function. A verify function only takes the results produced by Velox and nothing else, and just uses that to determine correctness. For example, in cases such as approximate percentile, we can do statistical analysis of the data returned, or the results returned, and ensure it's in the right error bounds to determine its correctness. Whereas in some other case like array accent union, we use the compare API, which takes both the computed results and the verified results and uses that to determine correctness. For example, in the array accent union, etc., results should be similar, but maybe in a different order, right? And here we again use the custom verification to get with the compare API to determine that the results returned from Velox and the reference DB are correct. We can check each of them and validate that they are same. And we use these tools to get a high level of confidence in our testing. And with that, let me hand over to my colleague, Wei.
Hi, folks. Yeah. Thank you for Krishna and Guy for the previous introduction. So now let's talk about the window fuzzer. In addition to the hash aggregation function that is tested by aggregation fuzzer that Krishna just talked about, aggregation functions can also be used in the window operator, along with the window specific functions. Therefore, we build this window fuzzer to test the window operation with these functions. We build this window fuzzer also with the help from the OSS community. So this window fuzzer, it generates random window queries with the random window classes, including the partition by, order by, and the window frame. It generates random queries in such a way that different code paths can be exercised in the window operator. For example, there is the code path for the sorted window build, and there is another code path for the streaming window build. Streaming window build is used only when the input data is already sorted on the partition by columns and order by columns. Also, there is the code path for the incremental aggregation, and there is another code path for the regular aggregation. The incremental aggregation is optimization that only applies when the window frame is expanding window frames. So I will talk about those in a minute. So let's first look at how we generate random window operations. We start by looking at this example of the window query. So suppose we have this table that is called the orders table. It has a column clerk and it has the column total price processed by this clerk on a day. And we want to calculate the rank of the total price in descending order for each of the clerk. So we can write this query. We select from the orders table. We first partition this table by the clerk, and then inside each partition, we order the rows by the total price in descending order. Then we call this rank window function on a range between unbounded proceeding, which is the start of the current partition, to the current row. So this would give us a rank results column that is the rank of each record for the clerk in descending order of the total price. However, this is just one particular query. We want the window fuzzer to generate random queries so that it can exercise many different code paths. So essentially, we need to let it execute a random function. We need to give it a random partition by class, a random order by class, and a random window frame. So all this colored part in this syntax are the things that we need to randomly generate. So first, let's look at the how we choose the random functions. Today there are 11 window functions in Velox, and so we test we like the window fuzzer to test all these 11 window functions with all the aggregation functions. The window fuzzer randomly determine whether it ignores nodes in the function argument if the function supports the ignore nodes. Later on, the fuzzer will compare the Velox results against the Presto. There are a few exceptions that I will talk about later. But among those functions that are compared against the Presto, some of the functions are order sensitive, meaning that the order of the input data to those functions affects the results. Although the result can be like both correct between Velox and Presto, they may not be exactly the same. So for those functions include all the window functions and a set of the aggregation functions that we have identified. So for those order sensitive functions, we make sure that when we construct the random window query, we always give it an order by clause so that the results from the Presto side and from Velox side can be deterministic. So let's look at how we generate random window clauses. First, we randomly generate 0 to 5 order by key columns and orders of them. For the order sensitive functions that I just mentioned, the randomly generated order by keys might have ties. So we want the order of input to be, we want the input data to be totally ordered. So in addition to the randomly generated order by keys, we always order by the row number columns additionally. We also randomly generate 0 to 5 partition by key columns. And then we randomly select the window frame unit, which can be a range, a row, or a group. And then we generate the frame start and frame end. And thanks to the open source community that help us to add these enhancements. Among the randomly generated window frames, some of the frames may be expanding frames, meaning that the frames of different rows in the same partition have the same window start, and then they have expanding window end. For those kind of frames, the window operator will take an optimization code path called the incremental aggregation. That just calculates the aggregation incrementally. So for those frames, the window fuzzer would exercise the incremental aggregation code path. And for the other frames, the window fuzzer tests the regular aggregation code path. Then we need to generate the random input data. We randomly generate the data for all the data columns, including the partition by keys and order by keys. We use the vector fuzzer to do it. There is a special handling for the partition by keys. We make sure that the size of the partitions are randomly determined between 1 and the batch size, so that some of the partitions can have multiple rows. This is to ensure that the calculation is not trivial. Some of the functions, they may not accept the totally random input data because they may expect some specific format of the data. For those functions, we use the custom input generators. Those functions include the min max by, the post functions, the map union sum, and some of the window functions. So for each group of those functions, we implement a custom input generator for them. So now we already have the random window query. We need to determine how to execute them. The query plan can be as simple as a basic plan that just gets the input data from the values node and then apply the window operation on top of it. We also generate 3 alternative plans that are logically equivalent. For example, instead of reading the data from the values node, we can also read the data from a table scan node. And then we can also sort sort the data by the order by and partition by keys first, and then do a streaming window operation on it. We make sure that after we get the results from the basic plan in Velox, we compare the results with the same query from Presto. We make sure that the results are the same, and then we also make sure that the results of all the equivalent plans are the same as the basic plan. There are a few exceptions that some of the functions, they require custom results logic, verification logics, because some of the functions, for example, the parser percentile, it uses a different parser algorithm in Velox from the algorithm used in Presto. So those results are not directly comparable. So we implement those custom result verifiers to make sure that the results in Velox is logically correct given the input data. So in summary, we substitute the non-deterministic functions in the Presto verifier with the deterministic ones to make sure that the query shape is correct by itself. So far, we have already added the support for the function substitution in the Presto verifier. It can be used with the -- function dash substitute command line arguments to specify the substitution patterns. On the fuzzer side, we have identified a list of bugs with the aggregation fuzzer and the window fuzzer enhanced by the Presto query runner. We have fixed most of those. We have fixed all of those bugs, except the last one that is rarely used, and we haven't got a chance to get to it yet. So for our next step, the ND function substitution can be further extended to support functions using the sketching algorithms, such as parser functions, and also to support other challenging functions like the row number window functions. On the fuzzer side, the window fuzzer need to support randomly generated key range frames. There is already a work in progress from the open source community. Some of the functions also require custom input generator that hasn't been implemented yet, and some of the functions require the custom result verifiers that need to be added in the window fuzzer and the aggregation fuzzer. There are also some work in progress. So with that, we conclude our discussion, our presentation, and we are happy to answer any questions.